Okay, everybody, welcome back. So for this next talk, we're going to be listening to, whoops, I lost it. Uh-oh, hold on a second. Tracing packets at OVS, an update on Retis. And our speakers are Paulo Valerio and Adrian Moreno from Red Hat.
Thank you. Hi, I'm Paulo, and today with Adrian, my colleague, I'm going to talk about tracing packets in OVS and provide you an update about Retis. Very briefly, what we are going to see is an overview of Retis, what it is, what it does, a mix of new and old features, some of the OVS specific features we developed, and a demo to show you the newly acquired capabilities. When debugging networking problems, you usually can go through different aspects, one of which is that packets go through multiple components. So for example, there is the kernel stack, there is vSwitch with upcalls, OVS, NFT, possibly, and so forth. And so retrieving context and informations related to these components is essential to have a better picture of what is going on. Also, a single system can process many packets at a given time, and so it's crucial to essentially narrow down what you see, because sometimes you're interested in a bunch of packets belonging to different flows or even a single packet. So having fine-grained filtering capabilities is essential. Also, last but not least, packet mutates. So if you see a single packet in a specific point of the packet path, this might not be the same as in a later point of the kernel of the stack. And existing tools are great, but sometimes are very specific in what they do. And so, for example, TCP dump and drop watch, and so you might want to require more of them, and and you might need multiple iterations to understand what's going on. Also, others are very powerful, but they provide you like building blocks on top of which you have to develop scripts and find your solution. Some others simply do not support OVS, for example. And that's why we designed Retis, which is exactly designed to enhance visibility in Linux with potential support of different control and data paths. It has built-in filtering capabilities. It can dump packets essentially from any SKB-aware trace point or kprobe or function, sorry. It can track packets and support OVS with upcall tracking and much more. It has different modules, it supports profiles, it can generate stack traces, it has multiple built-in post-processing subcommands. I suggest you to check out the documentation for more information about it. And given the problem statement, here's invoking Retis in this way. Retis invoked in this way, try to solve the problem statement. So essentially, it all starts collecting events. You can directly dump events as you receive them, or you can store in a file, and then post-process, or you can do both. Store in the file and print as they come. And this part of the command line essentially enables collectors, and collectors retrieve specific informations. Like, for example, the SKB collector is capable to collect information related to the packet itself, so L2, L3, L4 informations, plus metadata associated with the packet. The connection tracking module, the connection tracking collector, of course, it collects information. If there is an NFCT locally cached in an SKB, it's capable to retrieve those kind of information. So original directions, reply direction, zone, the city state, the protocol state, and so forth. Of course, some collectors instrument automatic probes, some others don't. This is the case of the SKB collector. It doesn't do that, but others do. And the remaining collectors are OVS. We are going to see more in the next slides. The NFT collector that essentially allows you to see a packet as it goes through the NFT rule set, and the SKB drop that reports drop reasons. The remaining problems are tackled essentially by two components of Retis that operate together, and those are filtering and tracking. Essentially, when a filter gets matched, the packet starts to be tracked, and so any manipulation that happens to the packet does not prevent you to receive events from collectors. So the packet still is tracked, and you still receive events related to the collector you enabled. And filtering is, and so for example, let's say if NAT happens as NAT, DNAT, or encapsulation, you're still able to collect events for that packet. Filtering is further split into parts. Packet filtering, which essentially allows you to express a pickup filter expression to match a packet, like, for example, as you do with TCP dump, and you can, do it essentially anywhere in the kernel. And metadata filtering. Metadata filtering is essentially a way to match against SKB members, SKB fields, and fundamentally you can match against numeric and strings values, and of course you can match against members belonging to inner data structure referenced by the SKB itself. It also supports advanced expressions like this one, which is equivalent to the one to the line below. So essentially, you can do, in this case, we are matching the CT mark. And on top of this, you can specify your own probes. The user can say what are the probe points the collector should be collecting events. And you can specify, for example, the option --p. You can specify it multiple times for each probe point we want to define. And of course, there is wildcard support to reduce the number of options. And events are stored in JSON file. To further reduce or to provide the user the ability to share essentially configurations, profiles are possible to be defined. And so what you need to do is essentially, we shift some of them with the tool, but you can also generate your own. And you have to define a YAML with, as you can see, the list of probes, options enables, collectors enables, sub-options related to the collectors, in this case, device informations for the SKB collector. And it also has further capabilities. You can add conditionals, so you can enable probes in a specific version of the kernel. So for example, symbols are present in a specific version of the kernel, and so you can attach eBPF programs to those symbols. And you can even say, okay, attach an eBPF program only if a probe exists. Narrowing down to OVS, okay, these are the main options to enable OVS tracing. And the OVS collector essentially loads eBPF programs to specific places of the kernel data path. And the OVS track option instead allows you to essentially tells Retis to load eBPF programs to the USDTs defined in user space, in the user space part. And of course, this requires USDT probes to be, USDT points to be, and USDTs to be enabled. And so you have to compile the user space part with the enable USDT probes flag. And this way, you are able to follow packets through the data paths and through up calls and back to the data path. This is essentially an overview of the point that Retis, where Retis loads eBPF programs. As you can see, there are trace points, KRoT probes, USDTs. There are further probe points we are going to see with an additional option to Retis we are going to see in the next slides. And once you've done collecting all the events you require, you essentially might want to post-process data, and Retis has built-in capabilities to do that. For example, one of the commands is sort. Sort essentially group events per packet, sorted, of course. And as you can see here, the packet is hitting this trace point, the upcall trace point, then it gets received to user space. it arrives to user space, and at some point, user space operates an execution. And as you can see here, the action, associated action, or if there are multiple actions, you are going to see multiple actions is shown. Another interesting post-processing command is the pcap post-processing. For example, the way it is invoked here, essentially extract all the packets hitting this trace point, generating a pcap ng file that you can then feed your favorite tool to, of course, see the content, the packets extracted. Every packet is essentially annotated with the trace point or the symbol, more generically speaking, the packet got extracted from. And now Adrian is going to introduce you some of the new cool features.
Okay, thank you. So one of the first features that I wanted to talk about is Python support. We have implemented Python support in Retis. It has 3 legs. First, there is Python bindings for internal Rust or Retis structs. There is a built-in shell, Python shell, and there is a Python library. So Python bindings start with the event object. So essentially, in the JSON file, when you try to parse it, what you get is a list of events. And an event, as you can see here, there's a built-in class called event, and it feels like if it's like kind of like a Python dictionary. So you can see if a specific section is present in an event, and you can kind of access it by just getting the attribute like that. You can list the sections with a specific helper called sections, and there is an interesting helper as well that is provided for in the Python bindings, which is the show command. The show command will generate the same string that Retis would generate with any of its existing like post-processing commands, like show, like print or sort that was shown before. Each of the sections have their own class that is automatically generated by Python bindings. So, for instance, if we have this SKB section, this SKB it has its own class. You can print it. You can access any of its members, and you can also show that that section of the event using that same helper. We have some bindings to read files. So you can create an event file, and you can read events from files generated by Retis. It's important to note that the sort command that Paolo showed before, the output of that can also be written into a file. So you can visualize the sorted events, but you can also store the sorted events in a JSON file. So you can read them as well. In this case, if you read a sorted file, what you get is what we call a series of events, which correspond to the same packet. And so you can iterate through the series as if it was a Python list. So it's a convenient way of reading both sorted and non-sorted events from Python. This allows you to implement basically any post-processing functionality that you may want. We have an embedded reader, an embedded Python executor. So if you call, for example, if you just write those simple 4 lines of Python, you save it into a file, and you run that command, Retis will execute it. So it will basically embed this reader variable, which is of the of type event file. So it's a very easy way of writing Python to process Redis events. If you don't specify any Python command, Python script, you will be dropped into an interactive Python shell where the reader variable is available. So you can do quick and dirty investigation, and maybe at some point write a script or whatever. Additionally, a Python library will be available in PyP. So you will be able to install it with pip install, and it's basically the same script, the same simple script that that was available before, but now you just need to add 2 lines. Basically, import the class event file and create it, point it to the right file, the event file that was generated by Retis, and that's it. You got your script. Now you can run statistics, in like run whatever you want on Redis events. We will be shipping pre-canned scripts, but if the community comes up with interesting examples, please let us know, and we will add them. And this is the another very important feature that I wanted to show today: OVS flow enrichment. So how OVS flow enrichment works? OVS will soon, this is unmerged, but I just wanted to show it. OVS will now probe this function for you guys. If you are not familiar with the OVS kernel module, this function is basically the table lookup in the kernel data path. So when the return value of this is basically the flow. So what this generates is an event with a UFID and a flow pointer and action pointer. This is fairly useless because it's a UFID. It's just an hexadecimal big number, right? But if you add this option to OVS, dash OVS enrich flows, what Retis will do is will connect to OVS via Unix control, so JSON RPC. And for each of those UFIDs, it will ask OVS, it will run dpctl get flow, and it will run OFproto dtrace, which is the tool that Dumitru and Alice presented yesterday. And connections are throttled because we don't want to, affect the data path and do any damage to OVS. And the results are cached for the same reason. And so this, with this option, it will generate events such as this. So this event, as a UFID, it has the data path flow, as you can see, and it has the open flow flows that generated this data path flow. This event in itself is also kind of not very useful because you don't know the packet, which packet hit this flow. But when you run Retis sort, then things start to make sense because you get the packet the first time you hit the packet and we started tracing it. You see the I've limited the output here, but you get the L2, L3, L4 headers. You get the contract information, NFT, whatever, and then eventually you hit the OVS, and the flow that the event that we generated on this probe is enriched with the open flow and the data path information. So it has some limitations. It's not perfect. Okay, so UFIDs the UFID is basically represents, it's the hash of the flow key. So the flow can be modified without modifying the UFID. So that's why we have the S flow pointer. Well, we have some extra pointers. Let's not get into details to just detect when the UFID is modified. It's important also to note that there is a limitation because we cannot really probe. We cannot easily get the UFID from the netlink, from the flowput USDT probe. And the reason is because the UFID is inside this flow struct. And we would need to know what the offset is. We don't have Cori in user space, so that's ideally we would add an argument there to get the UFID. And if we were able to do that, then we would be able to get this information also for app calls. And now let's go to the cool part. Here is the demo. Yeah. So this is an OpenShift cluster, okay, that we're debugging. I hope you can see. So we are running Retis in container. This is a script that is shipped with in the Retis repository. And what we're doing is filtering on the host IP address and a port, and putting all the commands using the generic profile, and also adding OVS flow enrichment. So here's the sort output. So let me pause it here. So what you can see at the top is curl. You can see the flow lookup stats, and you can see the packet information, as well as open flow and data path flows. You get all the actions. Packet is recirculated, so you get again the new data path flow and the new open flow flows. Packet is recirculated again, so you get another data path flow and another set of open flow flows. A lot of open flow flows. This is just basic OpenShift configuration. Okay, so open flow is complex, but you get all the information there, all nicely packed into a set of events that correspond to the same packet. You eventually then see the packet going out through one of the ports. Okay, so in this demo we are going to further analyze this trace, this set of events. We sort and we output the sorted file into a JSON, the sorted output into a JSON file, and we're going to run a Python script called ovnd trace, which is it hints a little bit. Maybe some already know what it might do. It's going to take the sorted output, and it's going to ask OVN for information about each OpenFlow flow. So now you get the packet information as it traverses the kernel, plus the data path flow, plus the OpenFlow flows, plus the OVN information, logical data paths, logical flows, and whatnot. There are plenty of talks. We have a talk in this same conference about it. So pretty neat. Another example of Python execution. In this case, we're running a Python script from scratch that what it does is it has taken a specific flow, and it has run OF proto trace So it's taken a specific flow, extracted the flow key, and run OF proto trace with it. So another example of using a very simple Python script, parse the Retis file, extract the information, and interact with OVS in this case to further enrich and further analyze the data. And that's it.
Okay, questions. I see Alice with his hand up. Let's go.
So first of all, this looks great. Thank you for working on this. And I have just one simple question. So you have the OVS enrichment. Do you plan to extend it with OVN enrichment, or is there any desire for that to incorporate the OVND trace in the output as well, like right away?
So yeah, we considered it. Doing it live, like doing it live, as in doing it in Retis as the events come up from the kernel, has some difficulties because we would need to access the database. Retis is written in Rust, so we would need the Rust OVSDB library. Already written one in Go. I really don't want to write another one. But yeah, and so on the other hand, the assumption is the OVN databases will be a little bit more stable. They will be, they will change slower, in a slower pace. So running a Python script as we did just after collecting the events, using the already existing OVND trace awesome script, kind of just the easiest path forward for that. So what we do plan is to upstream the OVND trace script. So it's basically a wrapper around OVND trace that just takes events from the Retis event file and just enrich them. So I don't know if it's if it's worth adding it live to the Retis processing.
Yeah. Okay, sounds good. Looking forward to it. Thanks.
Okay. In the interest of time, I think we're going to have to stop taking questions so we can move on to the next talk. So let's thank our speakers.